Okay, when Newton wrote down the three laws of motion, he did not try to derive the three laws from some fundamental principles. Okay, he just wrote it down, and somehow all these three laws are consistent with the experimental results. So they were verified by experimental. They were verified experimentally. Similarly, before the law of universal gravitation was put forward by Newton, Kepler also put forward the so-called the three Kepler's law based upon some observational data of the planetary motion, right? So all these are laws based on observations or are consistent with experimental data. Then one will ask, can we, or are there some more fundamental principles in the world from which we can derive the Newtonian laws of motion? All right, we'll ask, is it possible to derive the three Kepler's law based upon some fundamental principles? Of course, later we know that there exists the so-called universal gravitation. All right, Newton's law of universal gravitation. All right, so we can derive the Kepler's law very easily based on the Newton's law of universal gravitation and also the Newton's laws of motion. So then some physicists or scientists, they try to construct some fundamental principles in the hope that we can derive the Newton's laws of motions. All right, Newton's laws of motion, and also these fundamental principles will have a broader or more fundamental, broader in scope and more fundamental in nature. All right, so the fundamental principle that we are going to talk about is the principle of least action. All right. So first of all, let us consider a thought experiment. Okay, consider thought experiment. Okay. All right. Now, in this thought experiment, we consider a free particle mass m, which sets off a journey at x naught, t naught. So this is the starting point, space-time starting point, towards the destination or the endpoints at xf, tf. All right. Now we define a quantity called action. Okay, in terms of the kinetic energy of the system. Okay, and what does this action means? It means this action is the total sum of all the kinetic energies at every time point. That means if this is this straight line representing the trajectory of the particle, then at every time point, we have a kinetic energy. All right, at every time point, there's a corresponding kinetic energy, and we try to sum up all these kinetic energies along the path or within the interval from T0 to TF. Okay, and we call this total sum an action. Okay, the action of the particle. Now, then we, of course, if we do not know anything about Newtonian mechanics, then we just look at experiments to verify the results. Then I try to ask the students which path will the particle follow in this space-time space-time diagram. Then some student will say, yes, it followed the red dash curve. Another student will say it will follow the purple one. And also another will say, no, the green one will be the correct one. Of course, I point out that it goes along the black straight line. All right. Now, so which one is correct? Which one is correct? Then we all know that if a free particle is moving in space, it will follow a straight line. Am I right? It follows a straight line. So it should follow this black straight line. This is the path predicted by Newton's law of motion too. Okay, so what insight do we get from based upon this quantity action? Now, among all these different paths, we know that each path will give you a different action, S. So S for the red path, S for the purple path, S for the green path, S for the black straight line. Okay, so we compare them and we find that the Newton's trajectory or the classical path determined by Newton's law of motion has the smallest value of S, smallest value of S. Okay, so here is the so-called Lee section principle. The correct path for a free particle moving in space should be the one with the smallest or minimum value of the action is the one corresponding to a minimum value of the action. All right, so that is the so-called Lee's action principle. But this is only a proposal. This is only a proposal, right? So we would like to see whether it really works for other cases. Okay, so it works for free particle because the integrand of this integral contains the kinetic energy, and we know that this integrand is positive definite or non-negative definite, non-negative definite. All right, can you follow me? Okay, so it is very easy to see that the classical path corresponds to the path with the minimum value of the action. Okay. Some student will ask the following question. How do I know the kinetic the action corresponding to the classical path determined by Newton's laws of motion will give the minimum value of the action? How do we know? Can anyone give us very simple argument? Can any one of you give a simple argument to this question? Jerry Leung, can you try? Tai Chun Hei, can you try? Do an experiment. Of course, you can do that. Yes. Do the experiment. So you just measure the kinetic energy at every point and then add them together, right? But we are doing a thought experiment. Can you give a simple argument to answer this question, to convince the student that that is really the case? Now, shortest path doesn't mean that the action is minimal. Conservation of energy doesn't imply that the value of the action is minimum for the straight line. Am I right? So please, I hope that all of you will try. This is a very interesting question. You should be able to give a very simple argument to convince the student that the straight line corresponds to the minimum value of the action. Yes, velocity is constant. You can do that. Okay, no work done is needed for constant velocity. How about say something? I would like to hear your voices. All right. Trần Nhân Mong, can you tell us how to construct the argument? Hello?
So if we let the velocity is constant, then the integral is just time, just integrate the time. So, and in constant velocity, then shortest distance means shortest time.
Okay. All right. Now, let us come back to my question. Now, there is a student who has not studied Newton's laws of motion. He considered this thought experiment, all right? And he knows that a free particle is moving, all right, from the initial point to the final point, all right? Now, in his mind, he will say, he consider which one, he would like to find out which one is the correct path the free particle will follow. So there are 4 paths in his mind, and for each path, he calculates or he determines the corresponding action value. All right. And finally, I tell the student that it is obvious. The black straight line path will be the correct path because it gives the smallest value of s. Okay? The smallest value of s. So that is the principle I'm going to construct. But then the student get baffled about whether the black straight path really gives the minimum value of the action. All right. So can you help me to give an argument to convince the student? A simple argument. All right. No mathematics. Okay, it is a straight line, so the velocity must be constant. Am I right? So Kenneth Wong, can you try?
Guess the answer.
Yes.
I think there is something like about the work done, because when the xt graph is like the straight line, it means that the velocity is constant. Then the work done is not. The work done is minimal for them because there is no really change for
no, there's not. So far, we do not use the concept of work done. We have only one idea about the energy, all right, of the particle. That is the kinetic energy. Okay. My statement is that the correct path is the path giving the smallest value of the action. And that path is represented by the black straight path.
But Professor, if I cannot use the concept of work, but can I just use the concept of work? Because if I consider the particle is not moving, well, not exactly it's not moving, it's moving upward. And there's work done by the gravitational energy. And although all of the path has been done, well, there will be some sort of gravitational energy done on it, and it is same equal amount because the distance you move vertically is equal. But however, if we consider the straight path, like many before me said, because it is a straight path, there will be no work.
Hey. Remember that the student query about whether the black straight path gives the smallest value of the action. Okay, that is his question. How can you show him that this is in fact the case?
I think can we just show him the x dot versus t graph? Then it should be clear that the path with the classical path should take the least area in that graph.
He is only a high school student, all right? So it's not obvious to him. You have to convince him, okay, with a very simple argument.
Can you say because the velocity is not changing, it's like there is no force, so it's like not having to push a block? Can we say that?
But how about the other paths?
I mean, in the
Why
other
can't
part,
they? Why don't they give the smallest value of s?
oh, so because in other parts the velocity changes, which means there's some force for x, which means there's some acceleration. So he's having to apply some force, which will require him to do some work.
But the acceleration can be deceleration, right?
Yes.
So the velocity will be smaller.
No, but the overall the velocity has to be positive because well, it is gaining some distance and not going back, I hope.
Okay. Okay. Any other suggestion? Any other suggestion?
Maybe we can show him that just using 3 data points in this graph. So it's like the between the start and the end, there is only one middle point, and we can show him that if that point, the x drops down a little, and the slopes of 2 segments sum is larger than the straight line one.
Yeah, of course, for the curves, for the curving path, at some points, the velocity is smaller than the velocity of the black path. Some are larger, right? Some velocity are larger. But when you add them together, how can you guarantee that the black path gives the smallest value of action? In other words, the smallest value of the total sum of the kinetic energy at every time point. Now, before Newton, Galileo has already put forward the fact that, or the hypothesis that all inertial frames are equivalent. That means in every inertial frame, the physics are the same. Am I correct?
Can we say that we can use a frame that has the velocity of the black path, then we will see a black path not moving. If we chose a frame that has the same velocity as the black path. But for other frames, but because we know the velocity is changing, then there cannot be a frame that path will not have change of KE.
Yeah, you get it. So you go to the center of mass path, right? Go to the path of the moving particle along the black straight line. Then the kinetic energy will be 0 at all time point. So the total value of the action is 0. Am I correct? However, for all the other curved paths, the total kinetic energy cannot be 0. It must be non-zero. As a consequence, we can conclude that the classical path or the straight line path must give the smallest value of the action. All right? Do you get it now? Do you agree? We pick the frame co-moving with the free particle. So the particle is at rest all the time. So x naught equal to xf in that particular frame. So the total s, the value of s is equal to 0. Okay? So the action is 0. That's it. All right. So now we establish the fact that the assertion that the classical path of a free particle is the path represented by the black straight line, and it is the correct path determined by Newton's laws of motion. All right. So this Lee's action principle seems to be consistent with the Newton's laws of motion. Okay. Now we consider another example. Now we have a particle moving in a uniform gravitational field. All right. Now, how do we define the action? Obviously, we will try by similarity that the integrand should have an extra contribution from the potential energy. For the free particle, G is equal to 0. So we go back to the kinetic energy only. All right. So in this case, we try to propose the action should be defined in terms of the integral over time of the total energy of the particle. Okay. How do we find the correct path? The correct path, according to our Lee's action principle, the correct path should be the path that gives the minimum value of the action. All right. So to answer this question, we may compute the action for all possible paths, connecting the starting point and the destination, and check if the action of the classical path gives the minimum value or not. All right. So we just try every possible path. Then we can go let the computer to do it. And for each path, we assign a value to the action. And finally, we sort out the path corresponding to the minimum value of action. All right. And then compare with the path determined by Newton's law of motion. If they agree, then we are all set. The Lee's action principle seems to be consistent with the Newton's laws of motion. All right. But this is a very tedious approach and inefficient. So we'll ask, is it possible to have a more analytical approach without going through all these trouble? The answer is yes. We can apply the techniques of calculus of variations. All right. So what is the calculus of variation? All right. So if we are given a function of x, fx equal to x squared, and another function of x equal to e to the power minus x, then we can construct a function of a function in this way. The argument of the function of g, the function g, is the function fx. Okay, then this is a function of a function. Okay, after simplification, we realize that actually it is we'll realize that for each value of x, we would then assign a value to y. So y can be considered as a function of x. All right. However, a functional is very different. A functional takes a function as an argument. All right. Very similar to a function of a function, and assigns a number, assign it to a number. However, while a function of a function just looks at the value of the argument function, a functional looks at the entire behavior of its argument. All right. Now the difference is that now the functional would depend on the value of fx at a particular point x, but would not depend on the particular value, the value of x at a particular point of x, but the entire path of x. Here is an example. Here we define a functional g in the following way. This functional is the integral of the function fx over x from x equal to 0 to x equal to 1, all right? Here, y depends on the entire behavior of fx over the range x within the interval 0 and 1. If we use a different argument for the functional, say fx equal to square root x, then y will be represented by another integral, right? It will be represented by this integral in equation 3. Note that if g were defined as this, then g would be a functional of f and a function of w. So the value of g depends this function f over the whole interval from 0 to w. All right. If w is given, say equal to 1, then the function of g will depend on the behavior of the function f at every point x. Now this has a form very much like the action. So we say that the action is a functional, all right? Now the action functional is given in equation 5 for this particular example, a particle moving in a uniform gravitational field, all right? Now the integrand function contains the kinetic energy, the sum of the kinetic energy and the potential energy, i.e. the total energy. Now the value of the action actually depends on the details of x, which is a function of t, and also the details of x dot, which is also a function of t, all right? So the whole path, or the whole path from t0 to tf contribute to the value of this action, all right? Not just a space-time point, it's the whole path, all right? So that's the key thing. A functional is different from a function. A function depends on the x value at a certain point. However, a functional depends on x throughout the whole path, okay? Now, how do we minimize this functional? We all know that if we are given a function, fx, we want to find the minimum, we just take the first derivative of the function and set it equal to 0, all right? That is an extreme condition. To ensure that it gives you the minimum value, then we have to consider the second derivative of the function, right? For the functional, we can do the same thing. So we consider a small perturbation or a small deviation of a given path. So we start with a given path xt, then we consider a small perturbation at every time point. In other words, we consider another path which are very close to the given path. All right. Then we would like to see the difference in the value of action between these two paths. One path is given, the other one is perturbed from this given path. So the difference in the action value is here. So path, this is original path, and this is the perturbed path. All right. So we find the difference between the two actions. The total energy is the integrand for the perturbed. The first term contains the total energy along the perturbed path. The second term corresponds to the total energy for the given path. All right. And here, I would like to point out that the delta x dot is defined as d delta x dt. All right. Then we apply the Taylor expansion at each time point. All right. So the difference between these two total energy is approximated by these two terms as the leading order, in the leading order, all right? In the leading order. So the next step will be to rewrite this second point due to the deviation of the velocity, all right? So we perform something very much like the integration by parts, or you consider this as a differentiation of two variables, all right? And this term are equal to this one, okay? So somehow is very much like a differentiate of a product of two variables, two functions, and you will get two terms. One term is this, the other term is this, all right? So the next step, we realize that this is a total time derivative. We can integrate it out and get this one, all right? And this one, the second term combined with this term, altogether will form this one, okay? Now, how about what is the value of this result, the second term? Now, since we know that all the paths will have the same starting point and the same final point, same destination, so there no perturbation or no deviation will be found at both T0 and TF, all right? So the delta x at TF and delta x at T0 must be 0. So this term altogether will contribute nothing, all right? So we are left with this. We are left with this. Now this quantity is very interesting. Now in order to have a minimum value of S for the given path, we must require that the deviation in the value of S due to the perturbation at every time point must vanish, okay? Then how can we get this integral to vanish? Of course, they're very complicated at first glance, right? Because they can be positive, at certain point it can be positive, and another point it can be negative, all right? So how can we fix this condition in such a way that the delta S equal to 0? Now the trick is here. The delta X is arbitrary. That means we are comparing any arbitrary perturbed path in the given path. All right. So since this is arbitrary, in order to have the total the integral to vanish, we simply require this integrand vanish identically, okay, or at every time point. So this is the necessary condition. If this is true, then we are all set, right? So just like the case of finding the minimum of a function, okay? So we require the integrand of this integral to vanish automatically, okay? Now we look at the total energy. The total energy is given by this, okay? Now first we differentiate the total energy with respect to x. What do we get? We get mg, all right? And we differentiate the total energy with respect to x dot, then we get mx dot, and then differentiate with respect to t, then we have mx double dot equal to mg for arbitrary delta x, all right? Now, we are in trouble. Obviously, we know that this is not consistent with the Newton's equation of motion. The particle is moving in opposite direction to the gravitational force, all right? So it will experience deceleration. However, here in equation 7, we find that the particle is accelerating by the gravitational force. So there must be something wrong, okay? So the above analysis seems to, there must be something wrong. So how can we fix it? Take a closer look at this, the whole analysis. It seems that if the plus sign in the integrand of the action functional is replaced by a minus sign, that means if we replace this plus sign by a minus sign, then we are all set. We will get a resultant equation of motion which is compatible with Newton's equation of motion. All right. So as a consequence, the appropriate definition of the action functional should be given by this in equation 8, given by equation 8. Instead of having the total energy as the integrand here, we have the difference of the kinetic energy and the potential energy as the integrand. And this quantity, we call it Lagrangian, all right? Lagrangian, the difference between kinetic energy and potential energy, all right? So let us modify or revise the Lee section principle. We define the action corresponding to a path of a particle in moving in the presence of an external force, all right? External conservative force. It is the integral over time of the Lagrangian, all right, which is defined as T minus V, kinetic energy minus potential energy, okay? All right. However, that is a necessary condition for a minimum of the action, a minimum value of the action. We have to double check whether it it is really the minimum, all right, instead of being a maximum or point of inflection. Okay, so we double check. We look at the delta st, delta S along the classical path. Okay, then the first term here, instead of total energy, we replace it by L. Okay, the Lagrangian. Okay, Lagrangian, and also this here is Lagrangian to see what we get. What you get is this. The first term gives you delta x squared, something proportional to delta x squared. The second term gives you delta x dot squared, all right? Delta x dot squared. And we know that delta the second derivative of L with respect to x dot is equal to 0. Sorry, the second derivative of L with respect to x squared, x is equal to 0 because the gravitational force, the gravitational energy is linear in x. Okay, so the first term disappeared. Then we have the second term only. And this second term, in fact, positive definite. All right. Since it is positive definite, then the delta S must be greater than 0. So the classical path will give the minimum value of the action. So yes, it satisfies the Lee section principle. All right, the classical path gives the smallest value of the action. Now let us go to a more exciting example, simple harmonic oscillator, to see what happens. All right. To move on, how about we take a break now, 5 minutes, and then we'll come back to this example, simple harmonic oscillator, to see whether the Lee section principle can be applied to this example to derive the correct equation motion. Okay. All right. See you in 5 minutes. Okay, let's start again now. Let's go back to take a close look at the equation 9. All right. Now, when we consider the delta S, we try to apply the Taylor expansion, right? So this is the first derivative, the leading order term. We have shown that in order to have the least action, the first order term will vanish. So these terms will go to 0. So the difference between the two total energies, or between the two Lagrangians, will be approximated by the second derivatives, as shown here in equation 9, the second derivative. All right. Now, for the second derivative, as you can see here, something is missing. The cross derivative. Am I right? The cross derivative. That means the rank L, rank X dot. And the increment is delta X times delta X dot. All right. That cross term is missing. Why is it so? How can I take that term away? The answer is simple, because if you differentiate the Lagrangian, which is equal to the difference between kinetic energy and potential energy, with respect to X first, and then x dot, you know that it must vanish. Or or the other way around, you differentiate x dot first and then differentiate x, it also vanishes. All right, because there is no cross term in the integrand. Okay, in the integrand, there's no cross term for the Lagrangian. So we don't have to consider the cross term in the equation 9. All right. And in fact, the Lagrangian depends on x linearly. So this term also vanishes. Only this term will survive. Only the second term will survive, which corresponds to something like the kinetic energy, deviation in the kinetic energy. All right. And we all know that this must be positive. Now, since it is positive, then we say that it is minimal. The action value should be minimal. The analogy, this is the analogy for the existence of a minimum for a function fx. If a function fx has a minimum value at a certain point x, the first derivative must vanish. The second derivative must be greater than 0, right? Okay, let's continue our discussion. Now in this example, we consider a simple harmonic oscillator. So we have the kinetic energy and potential energy, all right? And according to what we have derived above, the equation motion here, instead of E, we replace it by L, Lagrangian, all right? So the derived equation motion is given by rang L rang X minus d dt rang L rang X dot, okay? It is given from here, all right? Instead of E, we replace it by L, all right? That will give us the correct equation of motion. Okay, let's check. If we differentiate the L with respect to X, we know that only the kinetic potential energy term, it depends on X, all right? So it will give you Kx, all right? And then we differentiate L with respect to X dot. Obviously, only the kinetic energy term will contribute. And we have Mx dot. And then differentiate the result with respect to T. Once again, we have Mx double dot. Okay? And then we move it to the other side. So we have Mx double dot equal to minus Kx. All right? Remember that the Lagrangian is equal to kinetic energy minus potential energy. Okay? So you can see that, yes, once again, we according to the Lee section principle and also the definition, the correct definition of the action, the derived equation motion is in fact identical to the Newton's second law of motion. All right. Now, in this case, we want to examine the effect of the second derivatives, because the first derivative equal to 0. Then we look at the leading order correction in terms of the second order derivatives. Once again, here we don't have any cross terms in the Lagrangian. So the cross terms will not exist. So the first term, the second derivative of the Lagrangian with respect to x will give you M, all right? Potential energy will give you M, okay? And sorry, the kinetic energy. Sorry, I get mixed up. Here, this term will give you minus 1/2 K. Sorry about it. The second derivative with respect to L, of L with respect to X will give you K, minus K. The second derivative of L with respect to X dot will give you M. All right. Now we are in trouble. both terms are positive definite. Both terms are positive definite. But here we have the difference of these two positive definite terms in the integrand. In other words, sometimes the overall effect will be negative. Sometimes the overall effect will be positive. Sometimes the effect is 0. All right. And you sum them together. If we sum them together, we cannot really guarantee that the total sum is positive or negative or 0. Okay, there is no way to figure this out. We cannot really know. Okay, so in fact, the classical path does not give a path of least action. The classical path gives a path of stationary action. Okay, or the path is an extremum, corresponds to an extremum of S. Neither minimum nor maximum. Okay, we only know that it is an extremum. However, by historical reason, we just use the term least action, right? But in fact, it is not, the classical path does not give a minimum value of the action. It gives a stationary action instead. All right. So here is the details. Here is the precise statement of the principle of least action. The motion of a system of n particles is such as to make the action S for fixed T0 and Tf is an extremum, where S is defined by this functional. Okay. Now this is for n particles. When n equal to 1, we go back to our simple cases. Okay, so let's double check for small perturbations or for small deviations from the chosen path. The difference in the action value is given by this, the delta S. So we subtract the action value corresponding to the perturbed path from find the difference between the action values of the perturbed path and also the chosen path. All right. And it can be represented by this integral, by this functional integral. Okay, keep in mind that delta q dot I is equal to d delta q dot dt. All right. Again, we apply the Taylor expansion, and keep only the leading order terms, i.e. the first derivative terms. All right. And then replacing the second term by this, okay, differentiation of a function, differentiation, a product of two functions, all right. One function is round L round Q dot, the other one is a delta Q, all right. And then integrate all these terms. We find that this term corresponds to our total differential. So we can integrate it directly and get this, all right? Now, our delta Q must vanish. Delta Qi must vanish at the starting point and also at the destination, all right? So this second term all vanish. So we are left with the first term only. Okay. Once again, the delta Q is arbitrary. In order to have delta S vanish, the requirement is that all these terms must vanish identically, all right, in order to have a zero delta S, a zero value of delta S, okay? So in this way, we have derived a system of equation motion. And this system of equation motion are known as the Euler-Lagrange equations, Euler-Lagrange equations, all right? So here are some basic rules for you to construct the Euler-Lagrange equations, basic rules. Express the Cartesian coordinates in terms of the generalized coordinates, okay? So somehow we like to find the, we like to determine the kinetic energy and potential energy terms first, all right, in terms of the Cartesian coordinates. And then we try to relate the Cartesian coordinates with some more generalized coordinates. I call it Q, okay? And then differentiating these quantities, we will obtain the Cartesian velocity components, okay? And then we substitute these generalized coordinates for the Cartesian coordinates involved in the potential energy formula and also the kinetic energy formula, all right? Then finally, we can obtain the Euler-Lagrange equation motion, all right? So as a basic rule, whenever you see a new problem, set up the kinetic energy, potential energy in terms of the Cartesian coordinates. Even though this is not a very smart move, it's not a smart step, but it is systematic, all right? So express the kinetic energy and potential energies in terms of Cartesian coordinates. And then express the Cartesian coordinates in terms of those more fundamental generalized coordinates. It may be the spherical coordinates or cylindrical coordinates or more generalized coordinates, all right? Now, I will give you an example very soon. So these are the rules, all right? Let us go to, these are the rules that you have better follow. Now I give you an example. Let me close it now. Okay. Now, consider a particle moving in a plane, all right? We follow the systematic procedures. First of all, write down the kinetic energy in terms of Cartesian coordinates and also the potential energy in terms of the Cartesian coordinates as in equation 7. So we write down the Lagrangian in terms of the Cartesian coordinates. Obviously, we can derive the equation of motion by applying the Lee section principle, right? And we get mx double dot equal to minus rang v rang x. How can I get this? I differentiate L with respect to x dot, and then differentiate the result by d with respect to t. Then I get mx dot. And also I differentiate the Lagrangian with respect to x. Obviously, that will give me the rang vx, rang v rang x. All right. So this is the equation motion, Euler-Lagrange equation motion in the x direction. And we repeat the same procedure for the y direction, all right? Now, here, you realize that this is a function of x and t, x and y. So these two equations are coupled to each other, all right? Now, if we use polar coordinates, then we will replace x equal to r cosine theta, y equal to sine theta, right? So the Lagrangian will be given in this form. All right. And then we apply the Euler-Lagrange equation motion. We differentiate L with respect to R dot, and then differentiate the result with respect to T. Okay. And we also differentiate L with respect to R. In this case, we have two terms. One term coming from the kinetic energy, another term comes from the potential energy. In the theta direction, we differentiate the Lagrangian with respect to theta dot, and then differentiate the result with respect to T. And also we differentiate the Lagrangian with respect to theta. Obviously, only the potential energy contains the theta, right? Here, we have a very important quantity that is called generalized momentum. We call it generalized momentum, m r squared theta dot, all right? The momentum in corresponding to the variable theta, okay? And also the generalized force, round v round theta minus round v round theta. And you can see right away that the generalized momentum corresponding to the theta is the angular momentum. And the generalized force corresponding to the variable theta is the torque, okay? Now, in the case that V is independent of theta, in other words, this is equal to 0, the right-hand side equal to 0. What does it mean? It means that the angular momentum is conserved. It does not change with respect to time, right? And theta is called a cyclic coordinate. Hence, both the conserved quantity and its conservation law can be easily identified in the Lagrangian formulation. Now here we can see that instead of using x dot, x and y, i.e. Cartesian coordinates, we can use our generalized coordinates. In this special case, the generalized coordinates are the polar coordinates, all right? So we write down the Lagrangian, kinetic energy and potential energy in terms of the Cartesian coordinates, and express the Cartesian coordinates in terms of the more generalized coordinates, in this case, the polar coordinates, okay? So in this way, we have rewritten the L in a very different form, in terms of the generalized coordinates, R and theta, all right? And also the generalized velocity, R dot and theta dot. And then we apply the Euler-Lagrange equation motion to derive the desired equation motion, all right? A cyclic coordinate it means that in the corresponding equation motion, in this case, equation 12, the variable theta does not exist, okay? Does not appear in this equation motion. If that is the case, we call this variable a cyclic coordinate, okay? Why do we call it a generalized momentum or generalized force? Because this set of coordinates are not the Cartesian coordinates, okay? Not the Cartesian coordinates, not the coordinates that we are familiar with. And in the next lecture, we will see more examples. Through those examples, we will learn why those more general, those coordinates are called generalized coordinates, all right, or generalized momentum. Now, cyclic coordinate means that the coordinate, in this case, the theta, does not appear in the equation motion. Okay? Does not appear in the equation motion. We call it cyclic coordinate. Let's see. Let me go back to our previous lectures notes. Yes, this is good. Now, everybody pays attention to this example. We write down the coordinates, Cartesian coordinates, velocities. We can write down kinetic energies, right, in terms of the Cartesian coordinates. We write down the potential energy in terms of Cartesian coordinates, right? Now, the Cartesian coordinates can be expressed in terms of phi and psi, right? So the kinetic energies can be expressed in terms of phi and psi, phi dot and psi dot. Same for potential energy. In this case, the phi and psi are called generalized coordinates. Phi dot, psi dot are called generalized velocities. Can you get it now? So that's why we give it such a name. Okay? This is a very good example. And I will come back to this example to derive the so-called generalized momentum. All right? I will come back to this example next time so that it will make clear to you why we use that particular names. All right, so here in this example, we first write down everything, kinetic energy, potential energy, and also the Lagrangian in terms of Cartesian coordinates. And then we express the Cartesian coordinates in terms of some more fundamental coordinates, in this case, phi and psi. Okay, and phi and psi are now called the generalized coordinates. Okay, all right, is it clear? I think I will stop here. I don't want to move too fast, and hope that you can digest the materials more easily. Okay, any more questions? Any questions about the material so far? I have skipped these summaries here. I think you can read it by yourself. Okay, it's only a summary. Right, generalized coordinates are some general terms for coordinate systems, which is not familiar to us, okay, which is not familiar to us. And also different from the so-called Cartesian coordinates, polar coordinates, or spherical coordinates. Okay, those are very common. So in this special example, all right, phi and psi are the generalized coordinates. Form a two-dimensional generalized coordinates. Ying Chen, I don't quite understand your question. Can you say it? Can you explain it? Oh. Equation 9 in lecture 8. Okay, equation 9. Is it here? So this is rank V, rank Y, because in the Y direction, there are two variables, all right? Yes, in this case, theta is not, the potential energy does not depend on theta, all right? So that this whole term disappears. Or if the potential energy depends on x only, then y coordinate is cyclic, is a cyclic coordinate, all right? Just in case that v depends on x only, then y is a cyclic coordinate. When rank v, rank y equal to 0, that means the momentum in the y direction is conserved. So it relates to conservation laws. So very powerful.
So whenever I have something that is conserved and I can call it a cyclic coordinate.
Right, right. So if we have a conserved quantity in the x direction, then the coordinate x is a cyclic coordinate. If we have a conserved quantity in theta or in r radius, then r is a cyclic coordinate. Is it clear?
Okay, thank you.
All right, Ying Chen, I have to lecture notes.
Yes, I typed the question wrong because previously in the previous break, I asked about the equation 9, the 1/2,
Yes.
and I want to make sure if the 1/2 came from the Taylor is because of the
Taylor
should be
expansion. Yes, Taylor expansion.
1/2 f prime times the delta x squared.
Let me get back there. Oh, not here. Let's see. You mean here?
Yes, it should be the second term for the Taylor expansion.
Right, exactly.
Yeah, because I was confused because the left-hand side is only one delta. This is why I should it be 2 delta, like delta square or delta s, the left-hand side, because the right-hand side is the second derivative.
Right, and then you have a delta x squared, and then delta x dot square. So second order term.
Oh, I got it.
Right, square. All right.
Yeah.
Okay, good.
Okay, thank you.
Any more questions? Okay, two new messages. One by one. Okay, how about cyclic coordinates? What is the significance of not having it in the equation? Conservation law. Okay. how about conserve energy? Does it have a cyclic coordinates? No. Don't worry. We'll talk about conservation law and symmetry very soon. All right. Don't worry. We'll come back to this question very soon. If Lagrangian have minus sign for potential energy, does it obey conservation of energy? Yes. Yes. Okay. I will show you how the conservation law of energy comes about when we discuss the symmetry of the system very soon. It does not come from the Lagrangian, okay? It comes from a symmetry of the Lagrangian or the action, all right? So give me a little bit of time, then we'll discuss the symmetry and the conservation law based on Lagrangian formulation of classical mechanics very soon. Right? Any more questions? Let me reiterate this. Now here I have the summary. I hope that you read it again. As you can see, rank L rank X dot gives the definition of generalized momentum. Okay, generalized momentum. If we have n particles, rank L rank Xi dot give you the generalized momentum for the particle I. All right, that is the definition for generalized momentum. Okay, generalized momentum. Okay. So if we have a cyclic equation, then this part disappears. So the generalized momentum, the corresponding generalized momentum will be conserved. So this gives you a very powerful conservation law for momentum. Okay. Momentum can be angular momentum because it's generalized.
So we call that quantity momentum because if we compare this equation with the equation of motion in Cartesian coordinate, the thing inside the dt is like
yes, you can say that. You can say that. Yes, yes, yes. Or you can check the dimension. All right. You check the dimension, then you realize that yes, that is the momentum dimension. It has the dimension of momentum in the linear case and also for the in the angular case. Okay. There's another name for generalized momentum or generalized coordinate. Sometimes we call it canonical momentum, canonical coordinate. All right, some textbooks use that name. Canonical momentum, canonical coordinate. Okay, any more questions? No more question, number one. No more question, number two. No more question, number three. Okay, let us stop here and we'll come back next Tuesday and discuss about the symmetry and conservation laws. Okay, all right, see you next Tuesday.